So we're going to be talking about hypothesis testing and continuing this topic in week 11. So we're going to be conducting a hypothesis on a mean when sigma is unknown using the t-test. We're going to calculate variances or standard deviations using the chi-square test. And we're going to calculate the hypothesis using basically confidence intervals. So it's actually quite repetitious from what we previously did. If we have properly learned the foundations of hypothesis testing, this is just going to be quite similar to what we have done. So there's nothing new. But let's review what we've done so far in the course. So we've previously looked at the Z test, which basically compares the subgroup, the sample, to the group at large, the population. And this is when essentially sigma was known. So this is what we previously did before the test. Three styles of tests are, there's the two-tailed test, which is basically testing if a sample is different from the population. And we indicate that test with this not equal signs. The left tail test, this is testing if a sample mean is less than a population. And the right tail test, testing if the sample mean is greater than the population. So these are basically your, for the alternative hypothesis, your three choices. Now, remember, our null hypothesis is usually when it's equal to. Now, then we have the two conclusions. If the test statistics is beyond the cutoffs in the tails, we reject that null hypothesis. So we could kind of draw it like something like this, perhaps. This is for the normal distribution. And if it's in here, that test statistic, then we reject, the null. And in this area, we accept. So if the test statistic is within the cutoff body, so if it's in that cutoff body, we fail to reject the null hypothesis. So again, this is like a little bit of a summary. We already did this. So hypothesis testing and t-tests. So more often than not, so the standard deviation of the population is usually unknown. So the Z test is not typically used for testing the hypothesis involving means. So this is where the t-test is used instead. The distribution of the variable should be approximately normal, and there's basic assumptions that we make. So this brings us to the single sample t-test. So a single sample t-test is a hypothesis test in which we compare data from one sample to a population for which we know the mean, but not the standard deviation. So we don't know that standard deviation. So like this sigma is unknown. Versus the Z test where sigma is known. So this test is almost identical to the Z test, except in two ways. The t distribution is used to find the cutoffs. So this, instead of Z, we have T subscript C, and this is that critical cutoff region. So we use this instead of the Z distribution. So we look this up in the T table. And a t-test statistic is used instead of this a z-test statistic. So let's look at and recall the process for finding the critical t-values. So let's remember kind of what we did previously. So let's say we have a researcher and they knows the mean number of calories at our that a rat will consume in an hour if unlimited food is available. So a rat will consume. He wonders whether a new food will lead rats to consume a different number of calories. So he studies 40 rats. So we know, of course, okay, our N is equal to 40. And he uses a P level of 0.05. So is this going to be one tail or two tail hypothesis testing? Well, the person wants to know if it's different number of calories. So the key word here is different number. So this is going to be a two-tail test because we're going to have the alternative hypothesis asking us if it's different. So this implies a two-tail test. What is the degrees of freedom? Well, N here is 40. So 40 minus 1 is just going to be 39. What are the critical T values? So if we draw our little sketch here, we know our P level or basically our alpha here is going to be 0.05. So this means, and we know it's two tails, so we're going to have a tail here and a tail here. So 95% is going to be in the middle. And if you divide this number by 2, you have to kind of see, you divide this by 2, you get 0.025 for one tail over here. So this implies a 2.5%. And this is also then going to be 2.5%. Because again, there's two tails, 1 and 2. And if you add up the whole thing, you get 1. Okay. So let's look this up in the table. So as we remember the T distribution, this area, and it's always great to see a little picture because they could possibly potentially change. I've seen normal tables where the numbers are a little bit different where they calculate it from the center. Anyways, in this T table that I gave you, this is the T critical value. And this area under the curve here is our alpha. And it says so. The shaded area is equal to alpha for T equals to T alpha. So this implies the shaded area underneath this curve. And at this time, this is to the right, this particular one. Remember, the Z curve is to the left. So we're looking for the shaded area is equal to 0.025, which is this one here, because we're just looking for one tail and the other tail would be symmetric on the other side. So it would be centered here at, anyways, so we'll just look at this. And it was at 39. So our T value is going to be 1.96. So this is for the one tail, it's going to be positive 1.96. And then our other tail over here, due to symmetry, is going to be negative 1.960. Remember, it is kind of normally distributed and symmetric. So you're going to have that symmetry. Now, if we recall a student's T distribution, so to find this T value for our test statistics, we use the following formula. So this is that student's T distribution with N minus 1 degrees of freedom. If you recall, Z was just equal to our X bar minus mu divided by our sigma, our standard deviation. So that almost looks the same. Now we replace this sigma sometimes and we use the central limit theorem. So we divide by the square root of N due to the central limit theorem. So this part is because let me write a little note of the central limit theorem. Okay. Now, so what has changed here is essentially they're basically the same formula. So almost, except for what is different, do you notice? Well, here we're just relabeling it for the sample instead of the population, because S here is for the sample, standard deviation. And sigma here is for the population standard deviation. So they're basically, it's almost the same thing. So there's just properties of the student's T. We see that it's mound shape and symmetric, about 0. So we noticed from before, again, that's mound shaped and symmetric to about 0. There is more variable than Z. So basically it has heavier tails, if we remember. The shape depends on the sample size N, or the degrees of freedom, which is N minus 1. And as N increases, the shape of the T and Z distribution become almost identical. And we can see this in the table again, if you look at what happens when N gets larger. We see that basically T approximates the Z distribution. And you can see that in the table. And let's just see it. So back to the T distribution, as you see, as the degrees of freedom, or basically our N increases and get larger, basically, we see that it approximates like these numbers, 1.96, well, this corresponds to that 95% basic confidence interval where we have here in this 2 tails. And you know this number is similar, it's the same number as the Z 95% critical value. So you can see that for very large values, it's going to be normal. So we can use this property to create like this estimation testing procedures for the population mean. So this would be like another picture of this is the normal distribution. This is the T distribution. You see it's a little bit flatter. So the assumptions for the T test for the mean when a sigma is unknown, basically the sample is a random sample. Either N is greater than or equal to 30, or the population is normally distributed when N is less than 30. And then we use the T table to find the critical values for the T tests. Remember, for the degrees of freedom larger than 30, we could round down to the nearest table value for the conservative approach. So again, like this is the procedure for a t-test. And we can also do the traditional value, finding that critical value, or the p-value. They're one and the same, essentially. So we can state the null and alternative hypothesis and identify the claim. We can find the critical values using the t-table. We compute this test statistic and or the p-value. We can either choose this method or the p-value approach. Then you just make a decision, is this test statistic in the rejection region or not in the rejection region, and which And then we just essentially summarize the results. So again, just to repeat ourselves, so finding like this t-table, let's say we wish something with n equals to 10. So we find this in the table that cuts off 0.025 in the right tail. Again, it's right tail. So the degrees of freedom would be 9. So we look at this up in the row, this in the column, and we find our critical value here, 2.262. Here's some quick examples of the differences. So suppose we have like these critical values. So 2.321 where n is equal to 15. And let's say we have a right tail test. So our degrees of freedom would be 15 minus 1, which is 14. And we can like look this value up in the table to find the P approach if we wish. So we look up the degrees of freedom. The value here is 2.321. So it's between this number and this number, somewhere in between. So we look up the areas to find, so our p-value is in the shaded area. So it's going to be between these values. This is the smaller number, 0.01, and this is the larger number, 0.025. So it's somewhere between like these specific values. Because this is like the right tail, this is basically one tail because the question tells you this. So therefore the values so our p-value is bounded between these specific 0.01 and 0.025. For the next question, we can like look at essentially the t-value when it's a two-tailed test, when t, and remember it's symmetric, so it doesn't matter, this t value is negative 1.415 due to the symmetry of it. We can like look this up in the table. So the degrees of freedom, because it's n is 24, so it's going to be 24 minus 1, so it's 23. And our number is between here and here somewhere, specifically where we're not sure. So it's bounded between like these two. But if we recall that this is a two-tailed test, so we're going to divide that p-value divided by 2. So you can consider, so this negative 1.415 will be between the negative values as well because of symmetry. So because this is that two-tailed test, the p-value is between those bounds, but this time what changes is the p-value is divided by 2. So we multiply the left side, the middle side, and the right side by 2, and we get 0.1 is the lower bound and 0.2 is the upper bound. Now for the last one, it's the left tail. So our degree, and n is equal to 17. So our degrees of freedom, of course, is going to be then 16. And we're looking up this value in our table. So our degrees of freedom is 16. Our number is between this value and this value. We're not sure exactly where. So our p-value is bound because that is like basically the probability. And remember that is the shaded area underneath the curve. So it's going to be bounded between this value and this value, somewhere in between those two values. So we can go back. So, and then we see this is how we get like these bounded values of what our p-value is. So we can, this is the second approach essentially, which it helps us to analyze it if we wish to use that p-value approach instead of the critical value approach in order to solve the questions. So let's look at another example. So let's say a counseling center on a college campus is looking to increase the participation rates by having students sign a contract to attend at least 10 sessions. It is known that the average number of sessions attended by students from the entire campus is 4.6. And this is for, again, it's known that the average number of sessions attended from the entire campus is this. Okay. So we have 5 students sign the contract and it attains 6, 6, 12, 7, and 8 sessions respectively. Use the single sample t-test with 0.10 p-level to determine if signing the contract has increased the number of sessions attended by students. Okay. So the type of test, it's going to be a t-test. And so we want to know, does it increase the number of sessions? So does that average, is it greater than this number? So this is a t-test, so it's a right tail test. We could divide it into the population 1 and population 2. So in population 1, we have the college students who signed that contract. In population 2, we have all the college students. So we could, and I'm just writing it out. So we could let mu, our average, remember this is our average or a mean, is equal to this is equal to the mean number of sessions attended by population 1, which is those who signed the contract. Mu2 is the number of sessions attended by the population, so all those students. So we set up our hypothesis. So our null hypothesis is that they're the same. And our alternative hypothesis, and we can set this up in different ways, is that the mean number of sessions attended by population 1 is greater than the average. So this is this right tail test. So our mu is 4.6, which is given in the question. Now, these specific numbers, we could use Excel to find like these numbers. So in Excel, we can just simply like type in these numbers, those 5 numbers, and we can find like there's functions. So you just type it in here. So let's say we want S, or we want the average. So here in the formula bar, you say equals standard, and then the functions come up. So there's standard deviation for the population and standard deviation for the sample. Since we're talking about a sample, we might want to use this one. We click on it and we auto drag it down, finish the bracket, and press enter. And then we could, of course, round if we wish. We could choose to round this. If we were doing, so this would be for the standard deviation of the sample. The average is just, there's a function, of course, for the average. So this is average. And then we click on it and then we drag it down. Press enter, and it gives us the average 7.8. So instead of actually having to compute these the long way, we could just simply use Excel. And it'll be like a much easier than if we plug in the numbers. Just be careful that you don't use, for example, let's say we want to use a sigma, so this is of the population. Let's compare it just to see. This would be standard deviation of the population. And if we drag these numbers down, well, we get a different standard deviation. So the two are different. This one is for the population. And this one is for the sample. So it's just easy to use Excel instead of actually having to compute all of this. So that's how I got like these two numbers. I just used Excel. It's much more straightforward, I think. Now, once you have that, you know that the mean of X bar is just equal to our mu. So this is 4.6. And our X bar is just S divided by square root of N. This is just like basically like that central limit theorem. And we can compute this. This is 2.490 divided by square root of N, and we get 1.114. Now we know that this is essentially 90%, because back to the question, 90% is on this side. And if we want it to see if this is greater than our average of 4.6. So there's 10% in this side, and it's therefore one tail. Our N here, of course, is 5. So our degrees of freedom is going to be 5 minus 1, which is 4. And we can look this up in the table. So our degrees of freedom is 4. So our alpha here is 0.1. So it's just going to be right here, 1.533. So then we get our value, 1.533 is our critical rejection, our critical region right here. So then we compute that test statistic, that t-test. So it's just essentially the same thing as our Z that we repeated before. Again, instead of sigma, we're using S. So we can just compute this, plug it in all the numbers, and get 2.873. Now we see if we go back, 2.873 is like this number here is 1.533, 2.8 something here is 2.833. So this number is larger than this number. So therefore, we reject that null hypothesis. So we reject this null in favor of the alternative hypothesis. So it appears the mean number of times students sign the contract, attend the sessions is more than the general students. So those who sign the contract attend the sessions more than the general students. So after completing a hypothesis test, there's a more convenient way, or there's a convention essentially for stating the primary statistical information in a condensed, more convenient way. So the APA format for the presentation of statistics is basically this. We write the symbol for the test statistic, we write the degrees of freedom in the brackets, we write an equal sign, and then the value of the test statistic, typically to 2 decimal places. And we write a comma and then indicate the p-value by writing in one of the 2 ways. Now, I'm not really going to ask you to do such a thing, but it's just good to see it if you know. So if P is less than the value when we reach, so then we write it this particular way when we reject the null hypothesis. If P is greater than this specific value, when we fail to reject the null hypothesis. And we'll see an example. So state the primary statistical information in APA format from the counseling sessions example that we just did. So we did a t-test, so we write the t. The degrees of freedom is 4. This was the test value that we obtained, 2.87, and we round it to 2 decimal places, 1, 2. Now we rejected the null hypothesis. So this is this part. So P is less than. So we write P is less than, and then we write to what significance. So 0.1. So this is how we kind of write it in this particular way. Now, once we've, so this brings us to confidence interval. So give the 95% confidence interval for the mean number of the counseling sessions for the population of students that sign the contract. So back, let's repeat this question a little bit. So this was one tail. So if it were 2 tails, right, let's say it was 95% confidence, we want it in basically essentially 2 tails. So we are changing the question from 90% for 1 tail to 95% confidence interval for 2 tails. That means, of course, we've drawn this several times before, but you have this in 2 tails. So this implies 0.025 in one tail and 0.025 in the other tail and 0.95 in the middle. So we want this confidence interval. We've done this kind of before. So the degrees of freedom is 4. And of course, we can like look this up in the table to get this critical value. So the degrees of freedom are 4. So in the one tail, it would be 0.025. So this would be our value here, 2.776. So we get that, and we can create our E that we did before. So it's just our TC times S divided by square root of N. We found that critical T value. We have our S divided by N, and we get this. Then we could create our confidence interval. We have X bar from previously, which was right here, 7.8 that we found using Excel, minus E less than mu less than X bar plus E. And we can compute this whole number, which this should be a 3. So that's a 3, and we can compute this interval. So we get that interval that we're, this confidence interval. Great. So what does this kind of tell us? Let's go back to the question. So while we created this confidence interval, our parameter 4.6, well, is it in the confidence interval? Because it goes from 4.7 to mu to less than 10.9. So is mu when it's 4.6 in here? No, it's outside of the 95% confidence interval. So this kind of makes sense because we rejected that null hypothesis that this value for, believe it was a 90%. So 95%, it's still not in that confidence interval. So this is how it kind of all comes together with the confidence intervals. So let's look at the same situation, but ignore the population standard deviation, forcing us to perform a single sample t-test. So we're going to do the same thing. Suppose the population mean statistic test for GPA is 3.51 from a sample of 45 students that participated in discussion groups. They had a sample mean of 3.7. We now add the sample standard deviation, and suppose this is 0.52. Perform a single sample t-test using a p level of 0.05 in this two-tailed test. So now we're going to see if it's different. So just step by step. So the type of test here is a t-test because we don't have that. Sigma is unknown. And it's two-tailed because the question literally tells you it's two-tailed. We have population 1, so all students who participated and took the test, versus population 2, all students who took the test. Now, the mean is, of course, the mean GPA of population 1, and mean 2 is the mean GPA of population 2. And we're checking that null hypothesis is always the same. It's that they're equal to each other. So our alternative here is that they're different. You could put 1 or alternative. So we can compute this. So the question first gives us like this information. So it gives us that the mean is 3.51. Our standard deviation of the sample is 0.52. Our X bar is 3.7. These, of course, are the same, if you notice, at 3.51. And we can compute our S X bar, which is S divided by square root of N, that central limit theorem, and get 0.078. Now, again, the degrees of freedom is N, which is, I think, 45, divided minus 1, which is 44. Now, it's a two-tailed test with, because the question literally tells us, so 95% is in the center. So this means 0.025 in one tail and 0.025 in the other tail. We can, again, like look this up. We can find like this critical value for, so finding that critical value for what we've done before, we see it's 0.025, so it's going to be in this column, and we scroll down and we see that it's a larger number, so of course it's 1.96. So due to the symmetry, you have, we have 1.96 on this side and negative 1.96 on that side. So again, our last step, of course, is to compute that t statistics, which is X bar minus mu, X bar divided by S divided by square root of N. This is, again, that central limit theorem. And we compute 2.44. Now, 2.44 is, whoops. So 2.44, let's say, is over here, 2.44. So we, therefore, what are we going to do? We reject that null hypothesis. So this is where we reject the null, and this is where we accept, of course, the null hypothesis. So we're going to reject that null hypothesis because with this data, this test statistic is in this region. So this is why we reject it. the null hypothesis. So therefore, it appears that the mean test score for students who attended the discussion session is different than the mean score obtained by students on the t-test. Because if we just go back, since we're rejecting this null and we're in favor of this, that means that they're different. And so that is the majority of our talk, but we're going to just go through more and more examples just to make sure that we're clear. So suppose we have a medical investigation claims that the average number of infections per week at a hospital is 16.3. A random sample of 10 weeks has a mean of 17.5. So we can start on the side here, taking out some information. So, and it has a mean number. So a random sample of 10 weeks has a mean number of 17.5 or 0.7. The standard deviation, S, is 1.8. Is there enough evidence to reject the investigator's claim at this alpha equals 0.05? So we want to, so the investigator claims that the average number of infections at the hospital is 16.3. So the question is the investigator's claim, what is the alternative, that they're basically different? So the null is that they're the same, which is always what we write, versus that they're different. So this is therefore going to be a two-tailed test that we can see. And we calculate that test statistic with our information that's given. So x bar minus mu divided by s divided by square root of n, we calculate 2.460. This is again our two tails, because we know because of this is two tails. So we can draw like a little sketch. In the center would be 95%. Over here and over here, you're going to have 0.025 or 2.5%. And so you can look up 0.025 in this table. If we wish. 1 second. So the degrees of freedom are 9 because there was 10 samples, I believe, and we have 0.025 is what we're looking up. So we get 2.262. And so plus and minus are those critical values for the sulfate being 0.05 and the degrees of freedom being 9. So therefore, this value here is 2.262, and this is negative 2.262. This value is larger than this value. It's over, let's say, here somewhere. So it is in that rejection region. So therefore, we reject that null hypothesis. So there is enough evidence to reject the claim that the average number of infections is 16.3. So we can reject it. So we reject the null. Okay, some more questions. So the average 1 ounce chocolate chip cookie contains 110 calories. A random sample of 15, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So our n here is, of course, 15. I always like to do a little count. Different brands of 1 ounce chocolate chip cookies resulted in the following calorie counts. At this alpha equals 0.01 level, is there sufficient evidence that the average calorie content is greater than 110 calories? So the null is that it's equal to 110. It's always the same thing, versus that we're looking for that it's the mu is going to be greater than 110 because it says so right here. So the sample mean, and we could compute this using Excel if we wish. We could take a second to compute that. So the sample mean is equal to, let's say, this number. So we can just take that average. I'm just going to say use Excel. So we can compute that sample mean and that standard deviation respectively. So actually, let's try to do this. So here I just wrote down like the numbers in Excel. And then for the average, I just typed in equals, because in the formula bar, you have to write equals average. And then from those cells, you highlight essentially, and then you auto scroll all the way down to the bottom and hit enter. Here for the standard deviation of the sample, this is of the sample. Again, we write standard deviation and formulas pop up, if you can see. You choose .s because it's of the sample, not the population, and you auto scroll it and you hit enter. Now, so I would probably most likely give you like these numbers in a test. Like I wouldn't, or I would, since actually you're working at home, you could just use Excel in order to find those numbers quite easily instead of actually calculating them. Now we compute that test statistic. So once we have our X bar minus our mu divided by our standard deviation of the sample divided by the square root of 15, we can compute this. So we get 4.389. Now, we already know that's going to be a larger number because of whatever our critical value is, but we could find like this critical value, of course, in the table. So let's switch back. So at 14, 0.01 is right here. So it's 2.624. And you could draw like a little picture, but you see, obviously, this is much larger than that critical value. So it is obviously going to be in that rejection region. So we're going to reject that null hypothesis. So therefore, there is sufficient evidence to support the claim that the mean is greater than 110. More examples. So a physician claims that joggers' maximal volume oxygen uptake, sorry, there's some spelling. So a physician claims that the jogger's maximal volume oxygen uptake is greater than the average of all adults. A random sample of 15 joggers has a mean, more mistakes, has a mean of 40.5 and a standard deviation of 6 milliliters per kilogram. If the average of all adults is 36.7, is there enough evidence to support the physician's claim that the alpha equals 0.05? Assume the variables are normally distributed. And this time, like, let's look at a p-value method. So we were really looking so many times at the critical value method. This is just a little bit different. So it's exactly kind of the same setup, but we're going to analyze it with the p-values instead. So the null hypothesis is that it's equal to 36.7. The alternative is that, let's just read it again. So it's greater than the average of all adults. So that is the alternative, that is mu is greater than 36.7. So just try to pick out keywords. Then we compute that test statistic, x bar minus mu, divided by s divided by square root of n, and we compute 2.517. Okay, now what do we do? We want to use the p-value method instead to help us analyze the results. So our degrees of freedom is 14, and our t statistic, because we're doing a p approach now, is between this value and this value, which corresponds that it's bounded between like 0.01 is the lower bound and 0.025 is the upper bound. So this falls between like these two values in the table. So we just use that table here. So corresponding to the lower bound 0.01 and the upper bound 0.025. So our p-value is somewhere in between the two, but we know that the alpha is equal to 0.025. So this is all then therefore less than 0.05. So this means, which I said before, we reject that null hypothesis since that p-value is less than 0.025. That means there's not enough evidence for the null hypothesis. So there's more evidence in favor of the t statistics, or the alternative here. So is enough evidence to support the claim oxygen uptake is greater than 36.7 milliliters per kilogram. So the CHAI test for variance and standard deviation. So we use, and this is a bit of a repeat because we've done this before essentially, but just not with hypothesis testing. So we use the chi-square distribution to construct confidence intervals for a single variance or standard deviation before. Now we use the distribution to test the claim about a single variance or standard deviation. So it's essentially what we've done before. So this is a bit of a review. So characteristics of the chi-square distribution. All chi values are greater than or equal to 0. So that is where it begins. So they're all going to be greater than or equal to 0. So it's a little bit different from the other ones of the Z and the T distributions. The chi-square distribution is a family of curves based on the degrees of freedom. The area under each chi-square distribution is equal to 1, because all the distributions, all the probability distributions, that area is under the curve is always equal to 1. So that makes sense. And the chi-square distributions are positively skewed. And we can see that by like looking at a picture, which will come up. So the chi table gives the area to the right of the critical value. So it's it's a little bit similar to the t-test. The z-test, remember, gives us the value to the left. So for a right tail test, we just use the area under the significance level for alpha for this specific degrees of freedom. So this makes sense. For a left tail test, we subtract. So now it gets a little different. We subtract 1 minus alpha and use the area in the table for that value for a specific degrees of freedom. And for a two-tailed test, we divide alpha by 2 and use the area under the value for a specific degrees of freedom for the right critical value. And the area for 1 minus alpha divided by 2 value for the degrees of freedom for the left critical value. So this is for the left. And this here is for the right. Just underlining it, sorry, kind of messy. But, and we've done this before. So this is our chi-square. This is what it looks like. It's positively skewed, so it's not symmetric like the other ones were before. And all these values, so it starts at 0. Before, the other ones were in the middle of 0, and there was positive values and negative values, and they were symmetric. This one looks like this. So for example, the value of the chi-square that cuts off 0.05 in the upper tail distribution. So let's say this is 0.05. This is that area under the curve. At degrees of freedom is 5 for 0.05 is going to be here, 0.05. So it's just going to be that value of 11.07. So let's look at the critical values for chi-squared. So example, so the right tail test with, let's say we have 15 degrees of freedom. So it tells you the degrees of freedom in this particular question, and an alpha of 0.025. So the question gave us the degrees of freedom. It didn't give us n. So it told us that it was 15. And it told us that alpha was 0.025. So we just looked down this table, and here's the value of 27.488 right there. So we can write down that critical value of 27.488 for the right-tailed. What about the left tail? So the left tail, let's say we are given the degrees of freedom as 27 degrees of freedom, and alpha is 0.05. So for a left tail, what we do is we take 1 minus alpha. So this would be 1 minus 0.05, and we'll get 0.95. And now we look this up in the table. So 0.95. Go down this column to 27 and you get 16.151 right here. That's that value. So when there's a two-tailed test with 9 degrees of freedom and alpha is equal to 0.01, there's going to be a lower part and an upper part. There's going to be 2 critical values, because it's a two-tailed test. And they're not going to be symmetric either, because remember, it starts at 0 and the chi-square distribution is not symmetric. So it's a little bit more complex here, essentially, to solve. But we can do this. So we're going to have basically our alpha divided by 2. So it's going to be 0.01 divided by 2. We're going to get 0.005. And our other alpha, so it would be 1 minus alpha divided by 2, but we already calculated that. So it's 1 minus 0.005, and we get the other one. So then we look up these values in our table. So the degrees of freedom is 9, because it's given in the question. So we can look up one of them. It's 0.995 right here. So it's 1.735. And the other one is, if you go along the row, all the way to 0.005, it's right here at 23.589. So we just found those critical values for this two-tailed test. So you notice for right-tailed tests, it was pretty straightforward. Let's just repeat this. For left-tailed tests, we take 1 minus alpha, and we get that critical value. And for our two-tailed tests, we're going to have 2 critical values. And we compute them in this particular way. Now, for a formula for the chi-square test statistic for a single variance, we take n minus 1 times s squared, where this is the sample standard deviation, divided by the standard deviation of the population squared. So this is all repeated down here. So the sample variance and the population variance. So instead of saying, standard deviation squared, I could have just said sample variance, population variance. So let's see some examples. So a psychologist wishes to see if the variance in IQ of 10 of his counseling patients is less than, keyword, the variance of the population, which is 225. The variance of the IQs of his 10 patients was 206. So we know, so this is where we have to kind of be a little careful. So we know that S squared is equal to 206. And we know that N here is 10. And we want to see if the counseling patients that the variance is the keyword. So the variance, so is going to be like less than 225. We want to claim okay. So we know the null hypothesis is equal to, because that's always how we begin, versus that alternative. Here it is less than 225. Because it's less than, this is a left tail test. So we can compute our chi-square. We just plug in the numbers, n minus 1 times the sample variance divided by the population variance, and we compute that number. So it's just arithmetic. Then we do, because it's a left tail test, we have alpha equals 0.05. We want 1 minus 0.05. So we use 0.95, and we look this up in the table with this degrees of freedom. So 0.95, our degrees of freedom is 9, so it's 3.325 right here. So this value right here is that critical value. So we get that value of 3.325. So we could kind of sort of draw this. It's kind of skewed. So I'll try to draw like a little sketch to see this a little bit more clearly. So this is essentially that value that we found, 3.325. And we found 8.25 is, let's say, over here. I'm not sure where it is. 8.24 is over here. So it falls, so this falls in the non-critical region. So we do not reject that null hypothesis, because this is like on this side. So we're not going to reject that null hypothesis. So this area is where we reject the null hypothesis. So reject null. This is where we accept the null. So we do not reject that null hypothesis. So there's not enough evidence to support the claim. Let's see some more examples. So a hospital administrator believes that the standard deviation of the number of people using outpatient surgery per day is greater than 8. A random sample of 15 days is selected. And here is our data. At 0.10, is there enough evidence to support the administrator's claim? So again, the standard deviation is now what we're looking at. Before we were looking at the variance. Okay, and we have like this data. Is there enough evidence to support the administrator's claim? Assume, so we want to see that the variance or the standard deviation is greater than 8 versus it's equal, the null hypothesis that it's equal to 8. Now with this data, we could just use Excel. I just showed you how to do that to find what S is. So chi-squared is equal to n-1 times S squared divided by sigma squared. We can compute this using Excel. And we have to remember, because this is the standard deviation of the sample, to remember to square it here in this particular example. Now here, because it's squared, we square this and we get 27.4521. Okay, so we can like, So this is a right-tailed versus this was the left tail because of this. So we can like look this up and find that critical value. So 0.1 and degrees of freedom is 14. So there's our value of 21.064 right here is that critical value. So keep forgetting what the degrees of freedom are. 19. So let's look them up. So we have 0.025. And the other one is here. Oh, sorry. So 0.025 is right here, 1932.852. And the other one is here at 8.907. And we have those values. So we get our two values. Or so we get this part 907, we get 32.852. And you kind of see something from the example, like this makes it clear that there's no negative values for this chi-squared. Like this one, this value over here will be 0. And so it's just good to understand this. Now this value here is 29. So let's use a different color. So let's say this is 29.5. And this is the area where we accept our null hypothesis. And over here is where we reject our null, and we reject it over here. Okay, so since it's between these values, we do not reject that null hypothesis. So there's not enough evidence to support that claim. Now we could use, if we really wish, this p approach essentially. So we could find the p values for chi-squared at the right tail test, the left tail, and two tail tests. And we can like look these values up using the same kind of idea. So the right tail test where n is equal to 9 and a chi-square, and this is similar to the idea of how we looked up p values for the t test. We can like look these up. So the test is, in this case, a right-tailed test with degrees of freedom is equal to 8. So in this table, we look up what this number is between, and we can do this according. So our degrees of freedom is 8. So our value is between 17 and 20, somewhere in between here. We're not really sure where. So our p-value is going to be between 0.01 and 0.025. So that's what I'm really just saying right here. So our p-value is between like those two values that we just looked up in the table. For the left-tailed test, where n is equal to 23 and chi-squared is this, we can look this up also in the table. So the degrees of freedom is 22 and our value was 3 something. So that's less than basically this value. However, it's a right-tailed test. So it's going to be 1 minus 0.005. So it's going to actually be less than this value because it's right-tailed test. Sorry. Okay. So we see that it was a less than the value in this column of 0.995, but because it's a left-tailed and chi-square gives us the right tails, we subtract, we take 1 minus that value and get 0.005. So the p-value is less than 0.005. The last one, a two-tailed test where n equals 24 and our chi-squared is 12.733, our p-value. So we know that it's the two-tailed test because the question gives you, and the degrees of freedom is 23. So we can look in the chi-squared on the row labeled 23 and find 12.733 and see where it falls between. Now there's going to be a lot of values here. Record that. So it's between like these two values would be 1, or between these two values. So between 0.975 and 0.95. Okay, so I repeat that. So we get like these values because the p-value falls between them. But remember before we said we subtract like those values to get the other values where the p actually falls between like those specific values. So you take 0.95, 1 minus 0.95, we get that value, same with the other value to get what p falls between them. Because it's a two-tailed test, we multiply it by 2. So that's what it's saying here is, whoops, really sorry for flipping back and forth. So here, so when it falls on the left side of the table, each of the values must be subtracted. So it's going to be 1 minus 0.975, so 0.025. And the other one would be 1 minus 0.95, which would be 0.05. And since it's two-tailed tests, each must be doubled to find the interval containing the p-value. Like remember before we had to double it. So this means like it would be between these two and the p-value is less than 2. So we multiply everything by 2 to get 0.05 is less than the p-value is less than 0.10. And we kind of did this before. So a last example here. So a random sample of heights, let's say they're in feet, of active volcanoes in North America outside of Alaska are as follows. Is there sufficient evidence that the standard deviation in heights of volcanoes outside of Alaska is less than the standard deviation in heights of Alaskan volcanoes, which is this particular value. So use this alpha 0.05, and we could use a p-value method. The question says this. So the null hypothesis is that it's the same versus the alternative that is less than, because that's what the question asks. And we can compute some numbers here. So we could compute the chi-square distribution, which is n-1 times that sample variance divided by that population variance. And but before that, we don't have, well, we have this, but we don't have the sample. This is our sample, of course. We're missing the sample variance. So we can compute this simply again by using Excel, which I showed you how to do. If we want, we could just do it one more time. So if you type them in, you see, you type them in and you hit the standard deviation of the sample, and we get the specific number. So 5 is, so the degrees of freedom are 5, and our value is 4.23. Oh, sorry, I'm looking up the wrong table. So 5. So it's between 4.23. So it's between these values, 0.1 and 0.9. So 0.1 and 0.9, it's between like these values because it's somewhere in between these two values. So we get it's between like these two values. So our I'm just repeating myself. So the p-value is between 0.1 and 0.9. So the p-value is basically greater than 0.05. So therefore the null is rejected. So there is not sufficient evidence to support the claim. Because obviously p here is greater than 0.05. So so not reject. The null. Calculating hypothesis using confidence intervals. So I kind of said that earlier already this morning, but we're just going to repeat it. So to kind of drill it in your mind. So there's a relationship between confidence intervals and hypothesis testing. So when the null hypothesis is rejected in a hypothesis test situation, the confidence interval for that mean using the same level of significance will not contain a hypothesized mean. And that's what we discovered earlier when we did a particular example. Also, when the null hypothesis is not rejected in a hypothesis testing situation, the confidence interval for that mean using the same level of significance, it will contain that particular hypothesized mean. So when we have that confidence, and we did this previously. So the average one-way airfare from Pittsburgh to Washington, D.C. is 236. A random sample of 20 one-way fares during a particular month had a mean of 210. So that is our mean. X bar of 210. Because it's a sample. With this standard deviation of 43. At the alpha equals 0.02, is there sufficient evidence to conclude a difference between the stated mean of 236? So is it different? Use the sample statistics to construct a 98% confidence interval for the true mean one-way airfare from Pittsburgh to Washington, and compare your interval to the results of the test. Do they support or contradict each other? So this is what we've previously done. So we've done that null hypothesis of it's equal to 236 versus the alternative that is different. This is obviously clearly a two-tailed test. So we can compute that test statistic, which is negative 2.70, and we can find the critical values for a 98% value, or you could see where this falls into the region. So we see the degrees of freedom is 19. So it's 98%. So, and it's two-tailed test. So 98% would be in the middle. So 1% would be on one side, 1% would be on the other side. So we find that our value here, is going to be 2.539 for that test statistic. Now the p-value is between the value we found was 2.7. So it's between here and here. So it's between like this value and this value, between like those values if we wanted the p approach. Stop. So the confidence interval for the mean is given like this. It's just x bar minus t times s divided by square root of n less than mu less than x bar plus t, the critical value, times s divided by square root of 20. We calculate this confidence interval of 230. So 236 is not in that confidence interval. So back to our result here is that we reject that null hypothesis because that value, this value of 236, is not in the confidence interval. So there's sufficient evidence to conclude that there's a difference because this is outside. So the 98% confidence interval does not contain this value of 236. 236 is outside. Therefore, there is agreement between the results of the hypothesized test and the confidence interval. So it does make sense.